All right, so here we're going to take a look at this problem from our textbook, and we're going to kind of make a connection between the permutation and that choose number. So this one states that your basketball team has 12 players. Assuming everyone can play every position, how many ways can you choose 5 players to be on the court? All right. Now, again, here is this asking for just a way we can put 5 players on the court, right? Or do we want to fill out the different positions for these 5 players, and how many ways can I do that? Right now, if the question is simply, right, choose 5 of these players to be on the court, right, then I don't really care about the position that each one of them is playing, right? Then that becomes one of our choose questions, right? So it's just a set, right? So really I have 12 players and I want to choose 5 of them, right? And I can fill in the positions how I'd like, but here this is really all I care about is how many different ways can I put 5 players out there on the court. All right. So doing that using Pascal's triangle or the formula, which will actually look at the connection between that formula that I introduced earlier and this the permutation number. So that becomes 792. Right. Now, on the other hand, what if I do care about what position each player is playing, right? So here I have 5 positions on the court, right? The standard, or I guess classic positions, right? Point guard, shooting guard, small forward, power forward, center, right? Our standard position 1 through 5. Right now, if I care about the order here, right, where not just the 5 players, but which position they play, right, then that adds more of these lineups that I can throw out there, right? At least they're distinct lineups, right? So this would be done using the permutation number, right? Where it would be 12 choices here, right? And again, I can choose from all 12 since all 12 can apparently play any 5 positions. Then 11, 10, 9, and 8, right? For a total of 95,040. Right? Now the way to think of this is this first one here, right? We think of a set, right? So here, and again, sets are unordered here, where it matters where I place these players, right? So it's more of a sequence. Okay? So a set is more like a combination, right? The different combinations. Where if I have the sequence like I have here, then that involves a permutation. But there is a connection between these two numbers. All right, now remember this number here is the permutation of the 5 objects out of a total of 12. Okay, so that is that number here, right? And then we have our choose number here. Well, if we think of the connection here, right, these 792 here, they show up, or then out of these 9,040, right, 12 choose 5, those show up somewhere in those 95,040 different permutations, right? The only thing here is these, the permutation versus the choose number, right? The choose number, or the permutation, excuse me, I'm over counting the ones that are in the choose number. So what I mean by that is, let's say we'll just call them generically player 1, 2, 3, 4, 5, all the way up to 12. Let's say just for simplicity that I take the first 5 here, and that's one lineup. Right now, if I look at the permutations, then how I sequence them matters, right? So this would be different, right? And then this one again would be different, a different lineup in the set of permutations, right? Hence why that number is so large, right? These are 3 distinct ones. But in my choose number, these are all one and the same, right? It's just a set, right? So all these are, if I'm just choosing 5, these are all in the eyes of the choose number, the same exact choice that I made, the same exact set, right? Since the set is just a combination, it's unordered. Okay, well, so that means that, well, if I think of my choose number and choose k, well, I can think of these permutations, but this is a huge overcount, right? Or huge, I guess it depends on the n and the k. This is an overcount, I'll say. So this is an overcount. Well, how much did I overcount by? So if we look at our example here of the basketball players, if there's 5 of them here, well, I overcounted by the different permutations that I have here, right? And for 5 in particular, this is 5 factorial, right? I can keep going, right? There's more of these. In fact, there's 120, right? 5 factorial of them. So to get to the choose number, I have to divide out the different permutations of k. So I have to divide out by this k factorial. All right, and then we could see here the formula that I presented without proof last time, n minus 1 dot n minus k plus 1 over k factorial. Well, what I can do is I can essentially multiply by 1, where 1 is going to be n minus k factorial over n minus k factorial, right? And then in combination here, the top part now, I go all the way up to 1, so the top becomes n factorial over n minus k factorial over k factorial. Right, and that's our choose number that we showed in an earlier section here. Right, so that's kind of how we see how they're related, right? The permutations, right, where I'm sequencing the objects, so any change in the order here is important, right? It matters. Okay. All right, so here. Another way to think of this, let's say an example here, right? So again here, before we move on here, think of, if you're thinking of a sequence, then that is going to be a permutation. Right, so in the place that you put these objects matters, but if you think of more of a set, where you're just gathering these objects, then that's more of the combination. Right, so this P N K, a combination is N choose K. Right, so for example, let's say you invite 6 of your 14 friends to dinner. Right, just have room for 6, so you got to choose 6 of them, right? Again, right, doesn't matter how you sequence them, right? All I care about is the combination, so this would be a choose number, right? 14 choose 6, so 14 factorial, 14 minus 6 is 8 factorial, 6 factorial, again, we can do the simplification here, this reduces to 3003. All right, now let's say you want to set these at a table. Right now here, let's say it was a circular table. And don't let this fool you off. Just choose a seat here as kind of your starting point. So here, if you're going to seat these at a table here, right? So let's say what would be the different seating arrangements for all of your friends. Well, here, in this case here, that would be the permutations of your 14 friends for the 6 seats. So this would be 14 factorial over 8 factorial. All right. Again, here, where I'm coming from here, if we have n choose k is equal to p nk over k factorial, right, then now I have an alternate definition for my permutation number. that would be equal to n choose k times the k factorial. Okay. So again, you're removing essentially the unordering of it, right? You're multiplying in that k factorial, so it adds the order back in, right? So then this is just n factorial over n minus k factorial. Okay. All right, and then simplifying that, there's 2,162,160 different arrangements for your arrangements of 6 for your 14 friends. Okay, so again, these problems can be tricky, right? If we don't really understand what we're counting, right? So just make sure that we read those problems carefully, and again, always refer to, is it a sequence? Where I place these objects, is that important? Then it's a permutation. Is it more of a set? So I don't care where I place them, just how I choose them. Well, that's just a combination, and we use the choose number.